Alrighty then, corn children, children of the corn, we will be looking at a technique called rationalizing numerators. Perhaps you've heard of rationalizing denominators in the past. Well, today we are going to be rationalizing numerators. And you're probably asking yourself, well, when is this going to come up? I'm so glad you asked. Let's look at this example and see the need for rationalizing a numerator. All right, here's our question. It seems so small. Find the derivative of f for f of x equals the square root of x. Okay, it's such a teeny little function, the square root function. Let's have at it. All right, we're going to be using the definition of the derivative. Do you remember the definition of the derivative? I certainly hope so. If not, go find the video on it. Here we go. The definition is, of course, f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Yes, there it is. It's our friend. So let's use it with this particular function. This is the limit as delta x approaches 0, f of x plus delta x. We know that this means you take the f function, take the x out, and replace it with the x plus delta x. Here's the function, square root of x. I write square root of blank. In the blank, I put the x plus delta x. There it is. Yeah. Minus the original function, minus square root of x all over delta x. Now, when we have a limit approaching a number, the first thing we try is to fill in the number. I want to fill in delta x becomes 0. If delta x becomes 0, this is x plus 0, so that's the square root of x. Square root of x minus the square root of x is, well, 0. And the denominator is also 0. Oh no, 0 over 0. That does not mean we're done. That means we are going to attempt to factor, cancel, and plug back in. But there's a huge problem. See these radicals? It's preventing us from doing anything. They're tying together all the x plus delta x's and all the x's. Oh no, if only the radicals weren't there. Getting rid of the radicals is called rationalizing. We need to rationalize our numerator. See why we're doing this video? Yeah, okay. So how are we going to do this? All right, well, we're going to stop for a second and think. What? Don't do that. Yeah, I know. All right, so what's a pretty color? This is pretty. Okay, so just for a minute, let's stop and think. I don't want to stop and think. All right, let's suppose, just out of the blue, I have A minus B. And I want there to be squares involved. Not just roll with it, all right? I am going to remind you that if I multiply by A plus B, something interesting happens. When we multiply this together, we get A times A. We get A times positive B. We get negative B times A. And we get positive times negative is negative B squared. Silly ABs, those cancel out. And look where we end up. We end up with the difference of squares. Difference of squares. I end up with a perfect square and a perfect square. Back to our problem, wouldn't it be nice if these were squared? Because the radicals would go away. And no, you cannot just go willy-nilly squaring things. We have to do this legally. Well, what do you mean legally? Well, this is a limit of this expression. This equals something. I don't want to change the value of it. And if you just go around squaring stuff, you change the value of it. I need to find a way to get squares to show up without changing the value of something. Well, take a look at this expression again. If we start with an A minus B, and I want squares to show up, but I don't want to change the value, couldn't I multiply by a form of 1? If I multiply by a form of 1, I don't change the value, and I would get these perfect squares. There would just be a denominator to the problem now. Well, we already have a denominator. That's not a big deal. So here's the kicker, people. We are going to use multiplying by a form of 1, which doesn't change the size of our answer in this process. The trick is, what form of 1? Okay, so let's go back to the problem. I know you forgot what the problem was. This is how far we got. We have applied the difference quotient, the definition of the derivative. I'm going to write that down again. So I've got the limit, delta x approaches 0. We've done our little thinking, plus delta x. And here's what I see. This part is like our a. This part is like our b, and there's a minus. Now, we are going to multiply by a form of 1, a fraction that is the same in the top as it is in the bottom, okay? Now, what form of 1? Well, this is a minus b. We need to use a form of 1 that is a plus b over itself. So here's what it's going to look like. This is our a. This is the a. We already have the minus, so over here we use the plus and then the b. Do you see it? This is the a plus b. Now it has to be a form of 1, so it's the same thing in the top and the bottom. And what this is going to do for us is it's going to allow us to get to a form where we can factor, cancel, plug back in. Trust me, it will. All right, so now we've got this whole giant mess. We are going to multiply this out. And because I care deeply about you, one and one time only, I'm going to do all the terms. I mean, obviously the shortcut is just going to be a squared minus b squared. We know that's what this turns into, but I'll do the whole thing. All right, foiling the top together. We're going to have this radical times itself again. That's the a times the a. That will be the square root of x plus delta x squared. Yes, if you see it coming, go ahead and get rid of stuff. Now we're going to do the a times the b. It's positive and positive. It's an understood positive. So that will be positive square root x plus delta x times positive x. Now we're going to do the inner ones. One is positive, this one is negative. So it will be negative square root of x plus delta x. And then at the back, a negative times a positive is negative, and we have radical x twice. So negative radical x squared. Now, don't forget there is a denominator here. Don't throw that away. I know it's very exciting in the top, but don't throw the denominator away. Because my goal when I got 0 over 0 was to factor, cancel, plug back in, I am not going to distribute the delta x. I'm going to leave it factored. The goal was factor, cancel, plug back in. So I'm leaving the denominator in factored form. Do you see it right here? That's multiply, factored. Ooh. All right. So let's look at the numerator now. Do you see it? Do you? Yeah. All right, hold on. Limit delta x approaches 0. X plus delta x under a square root squared. The square and the square root undo each other. I get x plus delta x. X plus delta x. These are the same, but one's positive, one's negative. Those totally cancel out. See, I wouldn't want to be you. Hey, look at this negative. It's not in the square, so it's going to stay negative. It's not in the parentheses, it's before it, so it's minus, and then x squared, square root of x squared is just x. I know. Here's the denominator. Don't lose it. We're almost there, people. Almost there. All right, look in the numerator. Do you see what I see, shepherd boy? Those cancel. All right, so we are ready to factor, cancel, plug back in. Well, there isn't anything left. Well, yeah, there's this delta x. And hey, focus for a second. Some of you are screwing this up. Do you see that delta x? It is a positive 1 delta x, there is a 1 there. It is a 1 times a delta x. There's a factor of 1 and a factor of delta x. So now we have factored. It's a, do you want me to write it that way with little parentheses? It's factored. So, oh man, I'm missing the delta here. That delta x is there. All right, so now it's factored. Now we can cancel the delta x's. There's a factor of delta x there and a factor there. Factor, cancel. The 1 didn't cancel, still there. Now the plug back in. Delta x turns to 0. It gets closer and closer to 0. So close to 0 that it treats it like 0. So what's left? Well, we've let the limit apply. So now we just have a 1 in the numerator. Do you see the 1 in the numerator? It's not a 0 up there. It's a 1. And in the denominator, I have square root of x plus square root of x. Campers, you're adding, not multiplying. That's 2 of those. 1 plus 1 makes 2. All right. And this, ladies and gentlemen, is our derivative. That is the technique of rationalizing a numerator. We go from radicals in the top to not having radicals in the top. How? By multiplying by a very helpful form of 1. Enjoy that now.